Okay, I'm going to talk about some geometric property of polyhedra in the three-dimensional space. And the space of constant curvature is either Euclidean, spherical, or hyperbolic space. And each of them take a very important place in the geometry and topology. After the most rigidity theorem, each geometric invariant is topological invariant as well. And the most important geometric invariant is the volume and Chern-Simons invariant. The most natural method to study geometric structure on the manifolds or orbifolds and cone manifolds in general is their partition to polyhedra and vice versa, namely identifying faces of polyhedra to get the resulting manifold. According to Petronio and Epstein, such a partition always takes place in hyperbolic space. So we take several polyhedra and we choose some pattern of orientation reversing identification a pair of two faces. This yields three complex wiki oriented manifold except near the vertices. And the number of three manifolds go dramatically with some complexity of the description. And any manifold can be obtained from some polyhedron by pairwise identification of its faces. Such a polyhedron is called fundamental, and its volume is equal to the volume of the given manifold. Andreev published a classification of all three-dimensional compact hyperbolic polyhedra other than tetrahedra, having non-obtuse dihedral angles. Thorson geometrization conjecture states that each of certain three-dimensional topological spaces had an unique geometric structure that can be associated with it. And Thorson himself proved the conjecture for the case of Hankin manifolds using Andreev's theorem as a fundamental tool. And Grigory Perelman, mathematician from St. Petersburg, gave a famous proof in 2003, the proof of full geometrization conjecture. So, given polyhedron of any combinatorial type, it might be very hard to compute its volume. For the case of hyperbolic and spherical polyhedra, it's even more difficult. And an integral formula for the volume of simplest polyhedron, that tetrahedron in hyperbolic and spherical space was standing for a long time undiscovered. Now it's at the Riemann-Meitner formula or Sforza formula was mentioned in the last talk. In the Euclidean space, Sabitov showed that the volume of simplicial polyhedron is determined by its combinatorial type, and h length up to the finitely many possibility. Namely, its volume is the root of so-called Sabitov polynomial. It's unknown. It's the unknown of it takes place in the hyperbolic or spherical spaces. And so to study the polyhedron in the particular spaces, namely the Euclidean space, hyperbolic or spherical space, we have to put it into some model of the corresponding spaces. In the Euclidean space, it's just ordinary system coordinate. So it's that ordinary cases which we on the way work on school geometry. But in the hyperbolic case and spherical case, we have to put it in some modern. Namely, in hyperbolic case, there are several modern of hyperbolic geometry, such as Gradient modern, Poincaré disk modern or Poincaré half plane modern, and the northern or hyperboloid modern. And for spherical case, hyperbolic spherical modern in Rn or Cn, and or stereographic model. And working in this modern is on the way have many of technical difficulty because because it's on the way make it more complicated to and more higher dimension to work in the modern. And for describe a particular polyhedron, it might take many parameters to define some polyhedron in general. But and the more parameter we need to define polyhedron, the more complicated to work with it, and the more complicated to get the volume of the corresponding polyhedron. However, symmetry of particular polyhedron reduces the number of parameters, and it makes easier to work with. Then, when we have a model for polyhedron, we can use the tool by Slevely. It was mentioned in the first and the second, so the talk previously. It's just the differential of volume of some polyhedron with associated with its parameter like edge length and the dihedral angle. And this so for three-dimensional cases. And so there's a formula for higher dimension as well. So now, when we have using the Slevely formula, we have to know some property, namely the relation between the parameter which define the polyhedron. And for the loss case, it's that the relation between dihedral angle and the edge length. And in the hyperbolic space, the vertices of polyhedron can be laid on the infinity, and in this case, the sum of dihedral angle so around the vertices is equal to n minus 2 pi. So this the Weinberg trick in the three-dimensional case can describe as follows. So consider some polyhedron, and at the vertex of polyhedron, we can put some sphere, and the sphere intersect with the faces of polyhedron the intersection will be a polygon. And so in the picture, so that it is the sphere which lie in the center of this, in the vertices, and the intersection is some the intersection will be the spherical polygon. I draw it like a Euclidean polygon, but it's in reality it's the spherical polygon. And so we get here, and this polygon has the edge of polygon It is the planar angle of the corresponding faces at the vertices. And the angle of the polygon will be the diagonal angle of the corresponding polyhedron. And the number of sides of polygon is the number of faces in the place of vertices. And to get the relation between dihedral angle and edge length of the polygon, we can instead we can study the property in the polygon, the corresponding polygon spherical, instead of the three-dimensional model. We can investigate the two-dimensional model to get the relation between dihedral angle and edge length. And it gives we a tool to get the relation. Now I will talk about the particular polyhedron we have studied. Antiprism. For the case of antiprism, is that the polyhedron with the two equal regular n-gon in the top and at the bottom. The lateral faces is equally triangle. The antiprism has the symmetry reflector rotational symmetry. And the definition takes place in either Euclidean hyperbolic spherical space. And to define antiprism, we have to need two parameters. And in the ideal cases, was studied by Wisnin and Metnick in the case of ideal rectangular antiprism is due to Thorsten. And in the case of ideal antiprism, the dihedral angle is related by condition 2a plus 2c equal to pi, as the previously case in this. That's the particular case. And for the compact case, it's inequality holds, like 2a plus 2c greater than 2 pi, because this polygon is spherical, and in the ideal case, the polygon is degenerate to the Euclidean polygon. And for the n equal to 2, the n-gon at the bottom and the top is reduced to the an side, to the set, an edge. And for the n equal to 3, it is octahedral. And for the two cases, this was investigated by Abrosimov and me, and previously for Abrosimov, Kulina, and Metnick. So for hyperbolic antiprism, we use the Kelly-Client model, and in this, that's like in the vector space model, and using some property of scalar coordinate, scalar product, we can get the relation between dihedral angle and the edge length of antiprism in this model. And it takes several computation to get this relation in the, like we have to compute the normal vector, we compute to the edge length by in the system of coordinates. And we end up with some relation like that. That express the dihedral angle A and C in terms of edge length A and C. And using the Следите formula, we can get the volume as shown here. It's the compact integral formula for the compact hyperbolic antiprism. And for the case of spherical antiprism, we use a Wien metric, which I showed before, and we put some sphere, two-dimensional sphere here, and the intersection with vertices of antiprism will be some isosceles trapezoid. It is a spherical trapezoid, which the side is the x and z, which is the angles, planar angle here and here, and y is the planar angle of the here. And A and C is correspondingly the dihedral angle along the edge A and SC. And yeah, we have to, so now we consider the isosceles, physical isosceles trapezoid, which shown here, and study this in the two-dimensional sphere, so ordinary in the three-dimensional Euclidean space, we get a property in the isosceles spherical trapezoid, which express the relation between the side length to the angle in the isosceles spherical trapezoid. And this is the following relation, and it's quite symmetry between the x-length side. And again, we can, so using this property in isosceles spherical trapezoid, we can get the relation in the spherical antiprism between the h length A and C everywhere and the dihedral angle A and C. And again, we apply the Следите differential equation for this. We get the volume formula for the spherical antiprism, and you can notice that the formula for spherical antiprism is hyperbolic antiprism. It look very similar. That's changing some hyperbolic cosine and sine to the ordinary sine and cosine. And now, so we also study several other polyhedra, but I show here only for the hyperbolic compact antipodal octahedron, which the antipodal octahedron is the octahedron with symmetry, the central symmetry through the point C in the space. That is, we have the vertices V1 and vertex VC a symmetry with respect to the point C, and analogously for the V2, V4, V5, V6, V3. Now, so to define the hyperbolic compact antipodal octahedron, we have to define some kind of a pyramid. If we have a pyramid, V1, V2, V3, V4, V5, we can define the antipodal octahedron that symmetry with respect to the point C here. So we can, so for compute the volume of compact antipodal octahedron, we can forget the lower part of the antiparent octahedron, and we only consider the top part of this. And in the following part is a pyramid. We can divide it into some tetrahedron. Namely, we can divide it to V1, V2, V3, V5, and V1, V3, V4, V5, or another as well. But it is symmetry, so like in reputation between the parameters. So it is not. So it's not in particular we consider this partition or this partition. Here, and to define antiparent octahedron, we need 6 parameters: A, B, C, D, F, and E. Yeah. And when we divide these two into the tetrahedron, we have to, from the given parameter, we have to compute the other parameter of tetrahedron, namely maybe the diagonal x and y and z, diagonal x, y and z, and thanks to the symmetry of this octahedron, we can find a beautiful relation between x and y, z, and the given parameter a, b, c, d, e, f, and so after that we find the x and y and z, we can apply the formula for hyperbolic tetrahedron, and we combine this, we get the volume of hyperbolic antiparent octahedron, and the volume is shown here. It's just the sum of volume of two, so exactly 4, but the two type of tetrahedron. The first part is the first tetrahedron, and the second part is the second tetrahedron. And this reminds the formula for previously talked about hyperbolic tetrahedron in terms of x length. And we get a volume formula for antiparent octahedron. So I have shown some method to approach the problem of calculating volume of polyhedron. So is it using Slave formula or just divided the polyhedron into several tetrahedron and get the combine of volume. But all of this it has some obstacles that when we face with general polyhedron, it takes a lot of parameters to define the polyhedron, and the more parameter we have, the more complicated we get to get some relation between dihedral angle and the edge length, and we get a system of equation that is impossible to solve because it's not non-linear. It takes a lot of radical symbol, so we can impossible to solve it analytically to get the relation between angle and edge length, and this is the main obstacle of the problem. And yes, maybe in future we can find the other method to approach the problem as well. And I think I finished my talk here, and I hope I give you something to get home from my talk, and you get some useful information from this. Thank you.